Good afternoon. My name is Daniel Ness. I'm a professor at St. John's University. I'm a professor in the area of STEAM education in the Department of Curriculum and Instruction. And my talk today is entitled Identification of Emergent Spatial Thinking Skills, Coding Through Observations in Constructive Free Play Environments. Research in spatial cognition and STEAM has been demonstrated that spatial thinking skill is both an essential process in student success in science, technology, engineering, arts, and architecture, and mathematics, or STEAM subjects, and it has also been an overall success in the workforce. Given its strong relationship with the STEAM disciplines, spatial thinking skill is seen as a cross-cutting domain that traverses and overlaps several intellectual fields of inquiry. Spatial cognition, a cross-cutting domain. Evidence strongly suggests that young children have the potential of engaging in a much more robust, dynamic curriculum than the typical quote-unquote teaching environments to which they are often exposed. Moreover, research has shown that preschoolers and kindergarten children benefit greatly from active engagement in conceptual STEAM curriculum. Equally as important as an active and dynamic STEAM content curriculum is a strong foundation in the cross-cutting process of spatial thinking, as this has been shown to be an essential skill in most STEAM-related areas. While psychological research in the development of spatial thinking connected with STEAM concepts has become increasingly robust within the past 2 decades, it still remains incomplete in a number of respects. First, the corpus of research treats subjects more in terms of cognitive area of inquiry and less so as a cross-cutting process skill. Second, resulting from these shortcomings is the paucity of discussion of spatial thinking skills in national and international curricula. And third, given evolving spatial cognition literature, much of this research involves primarily children presented with predetermined tasks to complete. So, the main goal of this paper is to consider and examine the spatial architectural coding system, or SPARC, formerly known as SPAGAR. We are going to look at spatial codes for research and practice that can be useful for our work and analysis of young children's spatial cognition, specifically in STEAM. The research here will enable researchers to use SPARC as a means of developing knowledge concerning young children's spatial development in particular domains. In addition, practitioners will have the opportunity to implement SPARC as a way to understand their young students' propensities in emergent STEAM disciplines. In terms of methodology, the development of these codes evolved from examining the literature on spatial and geometric thinking and identifying specific characteristics of STEM-related conceptualizations used by STEM professionals themselves. At the same time, observation and analysis of video segments, in addition to hermeneutical debate, numerous discussions and considerations with other experts in diverse fields who are involved in naturalistic observation methodology, served as a type of bottom-up approach, which led to the development of the codes described. The procedure is similar to that of Herb Ginsberg and his colleagues, who developed their 6 mathematical category codes. in a very similar manner to this. With respect to this study, investigation was underway that reconsidered each of the 13 codes of Spagar. We continue by initiating a discussion about how the initial 13 codes of Spagar have been identified and examined through digital video analyses of 4 to 6-year-old children's block, Lego, and plank play. This is followed by a discussion of how further analysis that was undertaken as a result of this project transformed and added to any inconsistencies which may have been initially evident in the original coding scheme. Through this project, my analysis led to the discovery of 4 additional codes, actually more recently 5 additional codes, and the modification of 3 former codes, therefore reaching 18 codes in total. All right, so now we get to the first overarching code set number 1, known as spatial relations. So in general, we'll be talking about 2 code sets. So this is the first one. In spatial relations, we have 3 general codes. So the code set of spatial relations consists of 3 general codes. The first is symmetric relations, the second is figural relations, and the third is direction location. In terms of symmetric relations, we consider 4 types of symmetry in children's free play activity: line symmetry, plane symmetry, central rotational symmetry, and patterning. With line symmetry, the object of question is centered equidistant from the sides or quote unquote ends of a larger object or structure. I'm just going to define centering here, which refers to placement of object so that the structure demonstrates symmetric appearance. The second subcode here is plane symmetry, in which structures in 3 dimensions exist whereby one side of the structure is a mirror image of the other. The third is rotational symmetry, whereby the object of the structure appears as if it is being rotated around its axis, and it appears in the same position 2 or more times. And lastly, the 4th subcode is patterning, a type of symmetry in which the placement of a group of objects is arranged in a way that demonstrates a subject-imposed, rule-governed activity or consistent relationship, thereby creating an intrinsically or extrinsically derived pattern, also known mathematically as space group symmetry. Okay, so let's compare the Spagar system to the Spark system. Sorry about that. Okay. So 2 specific areas of focus with respect to modification of Spagar concern the symmetry codes and at least 2 architecture engineering codes. In rethinking the symmetry codes through hermeneutical debate and discourse, I widened the notion of the individual's evidence of symmetry and delved deeper into the specific transformations the child or older individual is engaging in. Accordingly, I identified specific transformations in addition to reflection, that is symmetry, in particular, rotations and translations. So, with respect to reflection, the renaming of the line symmetry and plane symmetry codes and merging them into one code named reflections was deliberated for modification. With respect to rotations, I modified the rotational symmetry code to encompass greater latitude in meaning by renaming the code to rotations. While rotational symmetry is described as occurring in children's constructions when an object of the structure appears as if it is being rotated around its axis, the notion of rotational or rotation can involve greater flexibility in that it does not necessarily always involve reflection. A new code discovered under symmetric relations is translations, which describes situations in which the child who engages in constructive free play demonstrates similar positioning of an object or group of objects which are moved from one location to another. Here's just an example of symmetric relations in action. Okay, so as we can see in the photograph of the child using two hands to build his structure, the subcode here is reflections. And the description is that this situation is an example of bilateral symmetry. The more generalized term for bilateral symmetry is point group symmetry. In other words, one side of a construction is a reflection or replica of the other side. Okay. Next code is figural relations. And figural relations has two subcodes, and those two subcodes are figure identification and shape matching. Figure identification has to do with the object that may be present in children's mental schema. For example, the use or activity with square or triangular-like or shaped objects. These tend to be, figure identification tends to be more assimilative. The next subcode is shape matching, which deals with the child's adjustment to newly introduced geometric properties. And shape matching tends to be more accommodative as opposed to figure identification, which is more assimilative. The next overarching code is direction location. Direction location involves words, gestures, or actions relating to navigation, place, or location. Deliberate evidence of making navigation explicit, or a situation in which a child uses prepositions of navigation or other symbolic means in expressing geographical location. It consists of two subcodes: navigating and proportional reasoning. In terms of navigating, language, for example, prepositions like over, under, behind, on top of, left, right, the phrase, the building of the track under the bridge or a bridge, or actions that exhibit directionality, or topos, which refers to location or localization. That all has to do with navigating. The second subcode is proportional reasoning, and in this case, this is the explicit demonstration of magnitude and comparison, or size and mass. All right, we finally get to the second code set number 2, and this is entitled Engineering Architectural Principles. All right, so from Spagar to Spark. So in the, again, with Spagar, which started around 2001 and evolved over time through 2018 and 2019, when after a series of analyses, we've concluded that there's more to it that children do in terms of their engagement in spatially related STEM activities. And so that's how the Spark Engineering and Architectural Principles came about from about 2019 to the present. And as you could see here, in Spagar, on the left-hand side, we have enclosure, foundations, trabeated construction, posting, engineering, and proportional reasoning. So in the architecture engineering domain, I identified additional spatial behaviors associated with the engineering code. To begin with, I considered the support codes, namely foundation, trabeated construction, and posting, to be more basic than the engineering code and not as complex. I then considered the term engineering as a code to be broad in terms of what might be involved in visuospatial constructive play object constructions. When I refer to visuospatial constructive play object, or VCPO constructions, I'm referring to constructions with things like Legos, blocks, and bricks, and planks, obviously. And emergent spatial behaviors. So accordingly, sub-areas of engineering that are in consideration as separate spatial behaviors are things on the right-hand side, subcodes that are considered, such as cantilevered construction, whereby a structure contains blocks or bricks that exceed beyond the vertical center of gravity. Another new engineering code under consideration is truss construction, which involves the making of triangles with VCPOs for supporting higher structures or levels. A third code under investigation is curvature construction, whereby the individual designs and develops curvilinear structures from rectilinear or cuboidal blocks or planks. Okay. So in terms of examples, we have these two young girls who are exhibiting the subcodes of proto-cantilevered construction, okay, which is an emergent type of construction showing cantilevers in the sense of the planks jutting out a little bit on either side, but more or less in a haphazard manner. As you could see here, the planks are also stacked. So stacking is another subcode here. And trabeated construction, which is defined as post and beam or post and lintel construction, that you could see being constructed by the girl on the right. Okay, and here's an example of an amazing construction. There's interestingly no inside enclosure, let's say, enclosure within this structure, but the structure nevertheless is quite complicated. It consists of 3 subcodes that, as after analysis, we identified. And the first is reflections, which is a spatial relations subcode. And as you can see here, there is a sense of symmetry, or this idea of a reflection, of a reflectionary nature. We could also see stacking in the sense of stacking planks one on top of the other. And unlike the previous slide, which showed proto-cantilevered construction, this shows evidence of complex cantilevered construction, because as we could see here, the cantilevers are highly stable and took a lot of ingenuity and a lot of work and toil of the child to put this together. And as you can see here, it is the symmetry is, even though there are cantilevers, the symmetry is highly remarkable in this particular example. This is an excellent example of a child who is engaged in the process of construction, showing evidence of a 4-way coding scheme. So as we could see here, this particular coding scheme shows examples of enclosure. As you could see here, there's enclosure within this house-like structure. Stacking, as you can see on the roof of the house. Foundation, which is somewhat evident at the bottom of the house structure. And trabeated construction in the sense of this post and beam and post and lintel idea, which is keeping the 4 walls of the house intact, more or less. Okay, so enclosure, stacking, foundation, and trabeated construction. Here's an example of a pretty elaborate structure that exemplifies an amalgam of both code sets, namely spatial relations, and engineering architectural principles. And altogether consisting of 5 subcodes. The first is reflections, and everything, as you can see here, each of the subcodes are directly pointing to the example in the figure itself. So reflections, stacking, which as you can see is in the center here, which is keeping the center of the plank structure intact and not tipping over. Posting as well, because the stack itself in the middle is essentially a post. Trabeated construction, again, which is this post and lintel idea, which we find in both of the side structures. And complex cantilevered construction, as you could see here on the edges, or the very right and left-hand sides of the structure. Okay, and here's a very nice example of an engineering architectural code set consisting of definitely 2 subcodes. The first is patterning, because as you could see here, there's a pattern scheme associated with the planks as the children have developed this particular structure. And it also involves the subcode of curvature construction. As you can see here, the children were attempting to emulate a model of the Colosseum in Rome. And they did a fine job using cuboidal structures, which namely are planks, and forming them into curves, or a more or less a curvature construction. And finally, this is a prime example of complex cantilevered construction, where the child who is engaged in this process of construction shows evidence of at least 4 subcodes. The first is stacking, the second is foundation, the third is trabeated construction, and the fourth is complex cantilevered construction. Okay, so there's stacking involved. There's a foundation, as you could see at the bottom of the structure. There's the trabeated construction idea of the post and beam on the right-hand side specifically, and the complex cantilevered construction idea with the step-by-step nature of the planks on the right and the left-hand sides. Okay, so all in all, here's a Spark schematic that demonstrates basically the hierarchical nature of Spark itself. And as you can see here, the 2 code sets of spatial relations and engineering architectural principles are evident. With spatial relations, on the left, we have the 3 codes of symmetric relations, figural relations, and direction location. And of course, each of those codes are divided into either 2 or 4 subcodes, which are listed. And in terms of the engineering architectural principles code set, we go straight into the subcodes, actually. As you can see here, there are 10 subcodes here. I also want to alert you to what it explains at the top of each of the subcodes. On the right-hand side, above the light blue subcodes, it says, spatial relations subcodes possess intra-level levels of complexity. And on the right-hand side, above the light red subcodes, we see engineering architectural subcodes possess inter-levels of complexity. So it's important to note that in the previous slide, I point out these differences of intra-levels and inter-levels of complexity, whereby intra-levels of complexity has to do with the complexity continuum within the subcode itself in question, and inter-levels of complexity concerns the gradual increase or decrease of complexity from one subcode to the next. All right, so as we can see again here on the right-hand side with the engineering architectural principles, what we have here is a gradual progression from um, uh, less complex subcodes at the top going down to more complex subcodes at the bottom. Whereas on the right-hand side, each individual subcode has its own levels of complexity, thereby calling it intra levels of complexity. All right, so here is the spatial architectural coding or SPARC system, which will be used and actually has been used as the SPAGAR system prior to 2019 that both researchers and practitioners will be using to examine children's everyday constructive free play notions of STEAM and the spatial ideas and that are embedded within those notions of STEAM. In conclusion, SPARC consists of 4 general codes and 18 subcodes and was developed and subsequently modified by the researchers with both a top-down and bottom-up approach. The development of these codes evolved from examining the literature on spatial and geometric thinking and identifying specific characteristics of STEM conceptualizations. Observation and analysis of digital video segments of children's speech and actions provided a large corpus of data. In this respect, the large data set from video analysis attests to the validity and development of the coding system. The content validity for the codes was additionally established by a panel of experts in the fields of architecture, science, mathematics, cognitive psychology, and linguistics. Further piloting of the SPARC coding system is necessary in order to identify precise codes that allow the researcher to verify the specific development of the child. Thank you.